Today we are looking at compositions both graphically and algebraically, and looking at some of the things that we discussed last year in Algebra 2 and going into a little more depth this year. So the first thing that I want to talk about is the notation. And so we sometimes say Fogg notation or Goff notation, and we read this as f of g of x. I much prefer this notation. F of g of x means the same thing, but I think it's way more visual. You can see right here where g of x is sitting inside the boundaries of the f function, so we're going to plug g of x into f. So when I work through problems, you'll see me, if it's in this notation, convert it to this notation. That's just one of those things. And so it could be this way, g of f of x, g of f of x. All right, so we're going to start out by looking at compositions of graphs, and specifically compositions of graphs in the context of a problem. So we have these two graphs. I'm calling this one f of x, and on this graph we have speed and we have oxygen used. We have units for each of our scales, and this graph is represent oxygen use versus speed. When we get over to this graph, notice we have time on the horizontal axis and speed on the vertical. So this graph is speed versus time. So they have some similarities because we can deal with speed in both of them, but I couldn't answer a question about time and oxygen by just looking at the one graph. So the first graph, graph A, shows a jogger speed with respect to time. According to this graph, after jogging for about 10 seconds, how fast was the jogger running? So we're looking at the graph, and we know after a certain time, how fast was he going. So when I'm looking over here, I'm looking at this with respect to time. So you can see over here in this graph time and speed. So after 10 seconds, when you go up to the graph, it's right about there. So I said it was about 1.1, and the unit was meter per second. Application problems always require units. All right, so then the next one, the graph B shows the jogger's oxygen consumption with respect to his or her speed. According to this, how much oxygen would a jogger jogging 1 m per sec use? So over here at 1, I'm going up to my graph. Sorry, 1, I'm going up to the graph to see where it is. It's a little before you get to the mark of 5. So I said 4L per n. Okay? Not everything can be described in just one graph or the other. Sometimes we may have to use information off one graph to be able to interpret information off of another. So in order to compose two functions, you take the output from the first function, and that would be the range, and use it as the input or the domain of the second function. So for instance, in this problem, we want to know after 40 seconds, approximately how much oxygen did he use. So after 40 seconds, how much oxygen did he use? So then what we do to find that is we go to graph F. We would, the jogger was 40 seconds, which is about 2.2 in the speed. And then we go to the other graph, G of X, we would do 2.2 speeds, and then I can read off the graph, so oxygen is about 16. And so what I did was I went speed and seconds, and then I went over here to the next graph to get the information I needed, and that's about 16 L per m. Okay, how much oxygen did the jogger use after 55 seconds? So I need to go to where we're jogging at 55 seconds, so that's graph F, and that was approximately 2.4 speed. And then I go to graph G, which remember was this graph over here, and then at 2.4 speed, I can find it's around 23 oxygen with L per m, and that is a bit of an approximation, so that's why I use the word about before the answer. So a couple of things I want to remind you about is when we're dealing with functions and working with functions, there are actually what we consider 5 operations. We can add, subtract, multiply, divide, and what we're doing today, which is finding compositions. So if you see this f plus g of x, that's how you would read it, f plus g of x. That means you're taking the function f with a variable of x plus the function g with a variable of x. So subtraction, then it would be, it looks like this, and I just don't want you to confuse this and think, okay, now I need to subtract them and then multiply everything by x, because that would give you a crazy answer. So then you have f of x minus g of x, f of x times g of x, f of x divided by g of x, and then you have your composition statement. So those are the 5 operations. So on this page we have 2 graphs, but this time we're not necessarily in the context of a problem. So we would start with f of 3. So we go to the f graph at 3. We configure that the y value is 4. And then we go to the g graph at 4, and we can figure out the graph is down here at -8. So for the second one, I go to the g graph and find -4. So the g graph find -4, and that's down here at -8. And then I go to the f graph at -8, and I can find my value at -7. And the last one, if I go to 0 on the g graph, which is here, I'm up here at 8. And then if I go to 8 on the f graph, then I'm up here at 9. So you can see we're using one graph to manipulate our way to the next one. Now let's take a look at what we do in compositions when we have equations that we're working with. So I have the equation f of x, g of x, and h of x, and I'm going to use those equations to work through some more composition problems. So the first one I have h of f of -7. Remember that means h of f of -7. So I'm going to take -7 and put it in the f function and get an answer. Then I'm going to take that answer, which is what this will represent, and put it in h. And so sometimes you can do these in your head to a certain extent, but we're going to make sure we have some good notation going on here. So the first thing I did is took -7 and put it in f. So -7 up here, that's 3 times -7, which is -14 minus 1 gives me -22. And then I take the -22 and I put it in h. So this is the h function over here. So we have -22 plus 1, which gives me -21, divided by 3 gives me a final answer of -7. So the composition of x of f of -7 equals -7. Okay? So the next one, there we go. The next one, I'm putting g into f. So I wrote down f, I inserted the function g, and now I'm going to go up here and I'm going to write down the function f, because that's what this is telling me to do right here. I'm going to leave an open space wherever the x is so that I can substitute what's inside my function right here. So here's what I'm putting in, equals, I said 3, left open space, minus 1, put in the substitution of x squared plus 1, distributed through, I got 3x squared plus 3 minus 1, and so that leaves me with 3x squared plus 2. Alright, so now we're going to look at this one. So I'm inserting f of x into h. So I wrote down the h and I put in what f of x was. And so then I have my statement that I started with and I plugged it in. So remember that this is a fraction. So I plug in for that x right there, 3x minus 1. So I get 3x minus 1 plus 1 gives me 3x over 3, and then that just leaves me with x. And finally, the last one, it looks a little strange because I'm plugging something into itself. So I write down f because that's what's out here. I plug in the f of x function, which is 3x minus 1. So then when I start working the steps, I get f of 3x minus 1 equals 3, because that's what's right here. I leave an open circle for where the x would be, minus 1. And so that's what I did right here. And I made the substitution that I told myself I was going to make right here in the problem. So then I get 3 times 3 is 9x, and 3 times -1 is -3, and -3 and -1 gives me -4, so I have 9x minus 4. In the next section, we're going to decompose a function, which basically is a fancy way of saying, I'm giving you the answer, tell me what the problems were. And so you can see right here the answer equation is going to be h of x, and it took the composition of plugging g inside of f to get us this h of x function. So as I decompose this, I want to figure out what g of x is, which is going to be what I call my inside function, and what f of x is, which would be my outside function. So this next example, the problem is right here, 3x minus 5 all to the power of 2. So I'm hoping that you can see with these parentheses here at a power of 2 that we're actually talking about a quadratic equation, but when I look inside those parentheses, I see a linear equation. So inside the linear is the inside function, which is g of x, and the outside function then is when you take all this out, it would just be x squared. So the next problem, we have a linear inside a square root. So the inside function, the g of x function, is 3 minus x, and the outside function is square root of x. So these aren't too bad. And then when I get to this one, it's a little more interesting because we have to remember that we have an exponent rule in play here. X to the cube raised to the power of 2 is 3 plus, it gives you the value 3 times 2, which is 6, which is what the power on that x to the 6 is. So I rewrote x to the 6 as x to the third to the squared. And that reason I did that is I saw that I had an x cubed here. So I know I have some interesting stuff going on there. So the inside function then becomes the x cubes that you plugged in here. And the outside function would be x minus 1 over 2 plus x squared. So being able to decompose the function. All right, so the last set of problems is finding the domain of compositions. And so it's a little more interesting. You have to look at the input function and you have to look at the overall function. So basically what we're saying is each item would need to have its own unique y value. So each x has its each y. And we going to look at the domain that was put together that works for that. So you have to keep in mind what each function needs, what x's it needs for its domain, and then you're going to look at the overall picture. Okay, so now we're going to go through these problems right here and look at the domain. Okay, so here's what you're going to do when you take care of these problems. You're going to definitely need to sit down and take a minute to think about what you know about the problem, okay? So here's what I have. Now we said there's 3 main areas we watch out for that can be problematic, but 2 of the big ones are square roots and fractions. And not only do I have a fraction here, but I have a square root inside of the fraction, so it makes it become a little more interesting. So what do I know? Well, I know since that radical is on top, that the square root of x has to be greater than or equal to 0 because I can't take the square root of negative numbers. I also know that I have a fraction here in the general form of 1 over x, which means x can't be 0. So one of the easiest tools I can use to help me figure this out is a number line. And in that number line, remember that above the x-axis are positive values, y values, and below the x-axis are negative y values, and on the x-axis are zeros. So let's use a number line to help us figure that out. We know that this is a fraction, and we know the square root can be greater than or equal to 0, but the square root is in the denominator of the fraction, which makes this a little more interesting because we can't take the square root of 0 here, because if we did, we would get 0, and that 0 would fall right on the bottom of the fraction, which is a big no-no. So I have to remember that this has to be greater than 0. And so when I'm doing a situation like this where I'm trying to decide when something's positive or not, that's when the number line comes into play. So the first thing I need to do is put the numbers on the number line that I'm going to use, and I get those values by setting whatever's under the radical equal to 0 and solving. Once I do that, I can set it on the number line. Now remember that this can't be 0, but this could be. So now I've got to figure out where starting at 0 and going to infinity would be here. So the last little thing here is now that I know what I have, I need to make it fit together, right? So if my 0 was right here, the top one said I could be using these things, but if I use these numbers back here, then I'm trying to take the square root of a negative number and they won't work. If I go above the 2, I get imaginary numbers, so that won't work. So only the places between 0 and 2, this area right here, would be where you would find your solutions in your domain. So to write the domain then, we're going from 0 to 2, 0 to 2, include the 0 because that's okay, it's in the top, and don't include the 2 because that isn't greater than. All right. right, let's move on to domain number 2, for example 2. So here's a fraction. So thankfully this time I don't have any square roots, so it makes the whole process a little bit easier. But what I do know is anytime I have a fraction like this, x can't be 0. So then the next thing I need to know is when would the denominator be 0? Well, that's going to happen when x is negative 5. And the reason that's a problem is we can't have 0 in the denominator of the fraction. So that's really the only number we have to avoid. So you can write your domain from negative infinity to negative 5, soft bracket, skip over, soft bracket, negative infinity, negative 5 to infinity. I prefer this one, and we use this one most of the time anyway, unless we're dealing with rational functions, but in theory that is a rational function. So just pay attention to how the question is worded and what it asks. All right, so example 3, f of x equals 10 over x squared minus 2x. So the first thing that I would kind of make a note here about is that this is not in factored form, so I would probably start out by coming down here and factoring it. So it makes it a little easier to work with what you know. So I know that this is a fraction, so I know the fraction denominator can't be 0. So then I would need to know when does the denominator make its appearance trying to become 0, and that's at my factored places. So at x equals 0 and x equals positive 2. So we know that my graph can't be, or my domain can't include 0, and it can't include 2. So I start over here at negative infinity, I go to 0, which is the smallest number. I skip over and go from 0 to 2, which is the next number. I skip over and go 2 to infinity. And that's how I work through a problem like that. Only 2 more. All right, so example 4. So you can see a notation actually is composition here. And you see, so you've got some interesting stuff going on here. Well, we do have a fraction, so we know that x can't be 0. And so what number is going to make my denominator 0? Well, let's see. If this piece right here is 2, so what's going to make some number taking the cube root of it gives me a 2? And that has to be 8. So 8 cubed is 2. 2 minus 2 is 0. So what that tells me is the only value that won't work on this particular problem is when x tries to be 8. So we're going to exclude that from the domain, and we're going to go from negative infinity to 8, skip over to 8, and go to infinity. It's always kind of interesting when you've got 8s and infinities going on there in the same problem. All right, last one. There are a lot of things going on with this problem. It looks like it's kind of mild-mannered, and in a lot of ways it is, because it's just a square root, and I'm not happy to deal with the square root in a fraction, and in fact I'm not even happy to deal with a fraction at all. So the first thing I would do to kind of clean this up, so I distributed the negative through, and then I collected my like terms. So I'm really looking at this graph right here. So what do we know? We know that square root of x has to be greater than or equal to 0. And because this is not a fraction, the square root of 5 minus x squared has to be greater than or equal to 0. So again, I'm going to pull out what's underneath. 5 minus x squared equals minus 5, x squared equals 5, and x equals plus or minus root 5. And so that's just me solving for 0. So those go on my number line here and here. Well, if I test values like negative 5 here, then I do negative 5 squared is 25. 5 minus 25 is an imaginary number, and that can be part of my domain. If I pick 0, which falls between the two roots, then I have 0 squared. 5 minus 0 is 5, and that's going to give me a positive value here. When I pick a number like 5 over here, I'm back to what was going on the other side. 5 squared is 25. 5 minus 25 is an imaginary number. So what that tells me is the only viable solutions then fall between negative square root of 5 and square root of 5. And it would include both of them because it was greater than or equal to. All right, so that takes you through several domain practice questions. That will take us to our next lesson, which is inverse. Thanks, guys.